So while you can find calculus in many, many walks of life, I'm going to focus on 6 main applications: research analytics, meteorology, business, music, medical, and engineering. Diving right on into research analytical applications, we're going to talk about manufacturing. So with manufacturing, companies will often use calculus to boost their revenue by improving their output and productivity. Using birth and death rates, we are also going to predict population changes. For both video games and animated movies, calculus is used to make 3D models and animations. We also have gradient descent, which is an algorithm that is used to train machine learning models to become more accurate, and multivariable calculus, also for machine learning models so that they can make predictive models. So, now a research analytical equation. I was going to show these to you in real time, but my recordings weren't working properly, so I went ahead and typed them out. For this one, if the initial population of a town is 60,000 and the rate of growth is 0.05%, how large will the population be after 10 years? Using this equation of P equals the initial population times E to the relative growth rate times T, which is going to give you 60,000 times E to the 0.05 times 10, which is approximately 98,923 people. For meteorological applications, we're going to have meteorologists use pressure changes, temperature, and humidity to detect and predict weather patterns. These are some examples I found online of meteorological calculus equations. These are 5 different examples of what they would use to describe the behavior of atmospheric phenomena. And our brain break, because STEM majors definitely feel this way on a regular basis. So, back to the presentation with business applications. Starting with credit card payments, companies are going to use your interest rate and account balances to determine what your minimum amount due and your payment structures are every month. In economics, we're going to use the supply and demand curve to find the price elasticity at any given point. And for both production costs and revenue and profit, we're going to use calculus to minimize those production costs and maximize your profit. So, this is another one that I went ahead and typed out prior to making this. So if a manufacturing company can make 100,000 bikes a day, and the total daily cost of producing X bikes in that day is shown by B of X equals 100,000 plus 0.03x plus 250 million over X, how many bikes should the company produce a day to minimize production costs? So first you're going to find B prime of X, which is going to get you 0.03 minus 250 million over X squared. Then you're going to find the second derivative of B of X, which is going to get you 500 million over X cubed. Then you're going to go back to that initial derivative and you're going to make it equal to 0, which is going to get you X is approximately equal to 91,287, plus or minus. But since we know that bikes are going to be positive and we're not going to be making negative bikes, we're going to go ahead and get rid of that negative and just say that X is approximately equal to 91,287. And using that second derivative, we know that the equation is going to be concave up as long as X is greater than 0, which it's going to be because we're only going to be producing bikes and not negative bikes, which means that the company is going to want to produce 91,287 bikes a day to minimize their production costs. So, now on to musical applications, because calculus doesn't just apply to STEM fields. For harmonics, calculus is going to be used to make adjustments based on friction and air resistance, allowing the best sound output. And for acoustics, we're going to compute resonance and forced oscillation. And we're also going to use sound waves in both of these applications. Now, these are some music calculus applications, equation examples. So these are some things that you might see when you are using calculus in the musical field. And this is our brain break part 2, and I decided that we should include some music in here.
3 o'clock in the morning. 3 in the morning is a good time for bongo. Was sleeping, laying and sleeps. Well, I play bongo. Oh, he doesn't. Let him sleep. Well, I play bongo.
And now we're going to go back into the STEM field applications with the medical field. And I personally really enjoy the medical field side of calculus just because I've seen how important calculus is to patient diagnosis, because they had to use calculus to diagnose me with my nervous system disorder based on my blood flow and everything like that. So it's really important. Moving on to bacterial growth, where calculus is going to be used with environmental factors to determine that bacterial growth rate. Patient diagnosis, calculus is going to be used to measure things like blood flow, cardiac output, tumor growth and shrinkage, and lots more. We're also going to use calculus in that drip rate. Calculus is also used in cardiology. We're going to be able to make artificial things for your body, like an artificial aorta, and we're going to be able to make sure that things are placed properly during your transplant surgeries. Cardiologists are also going to use calculus to understand blood flow. In neurology, we're going to use calculus to determine the voltage of neurons. Now, this is an equation for finding bacterial growth. It is a lot longer than just this part, and if you want to see the rest of it, it is in my sources at the end. Now, to our last application, my personal favorite, engineering. Going straight into structural, we have that calculus is used for structural analysis, calculating building heat loss, and determining the amount of materials you're going to need. In civil engineering, calculus is going to be used by civil engineers when building bridges, and they're going to be able to determine tension and compression along with the bridge capacity. In electrical engineering, we're going to use calculus to determine voltage and current through capacitors, along with like wire lengths and a bunch of other things. In mechanical engineering, we're going to use calculus for things like household items, vehicles, and many more things. In water treatment, engineers are going to use calculus to understand chemical reactions and help remove contaminants from the water. And in rocket design, we're going to use calculus for thrust and optimizing rocket trajectory. This is another equation example for calculus and engineering. So there's 2 different equations on here. There are also more in my sources at the end. And for our final brain break, engineers are just as smart as physicists, and I'm gonna have to go ahead and agree with Howard here. I'm not biased, but sorry, physicists. So I just wanted to take a minute to talk about how calculus has been in my personal life. I joined robotics way back in middle school, and we've been using even just like small amounts of calculus ever since then. Now in robotics, a lot of our calculus is going to go into programming. However, we're also going to use calculus when it comes to building the robot. So for this robot over here, the one with the rings, the little round rings, we were shooting these into like really small boxes, and we had to use calculus to determine the angle of the plate, how fast the motor needed to be, and the position on the field that we were going to be in to make sure we made it through that little box at the top of the field. We also used calculus to determine how fast we needed to speed up and slow down to get to our places on time without jerking our robots around too much. Some of these pictures are just pictures of robots I helped build, teams I was on, and an interview for the news. And these are my sources.